This is our next trick, or our next trick type question, where you're going to get a regular equilibrium problem, but you're going to have a constant velocity thrown in. So that, I'm trying to think of a situation that we could have this other than the helicopter question or something like that. So I figured we'd look at a Tarzan situation, except this time Tarzan's on a clothesline. And this clothesline is like a physics clothesline. When he's dangling off the middle of it, it doesn't actually deflect like it would in the real world. It's going to stay perfectly straight. And so we'll have Tarzan's going to attach his vine to this clothesline, and the vine itself is not going to actually move either. It's just going to be the clothesline, the physics clothesline that moves. That's enough about that. He's going to be some tension on his vine, like that. And Tarzan will be holding on for dear life, no doubt. And probably like that. Yeehaw. And what you're going to be told, and here's the trick, is that Tarzan's going to be going on his vine at some sort of a constant velocity. I'm going to put that constant velocity in red, and we don't really care what that constant velocity is. They'll tell you a number. They'll say he's going at 40 meters per second or something. We don't care about that. If it's going at a constant velocity, what that means is that you're going to have some sort of a frictional force backwards on him, air friction, keeping him from accelerating. Okay, that's what's happening. So he's sliding across to the right. Frictional force is keeping him going at a constant velocity, and you'll be given Tarzan's weight as well. You'd be given one of these things, hey, weight or tension. I'm going to give you tension. We're going to say that tension is going to be 11,000 newtons. But you know what? Before I get any further, I don't like the fact that there's an extra vector in here. I made it in red, but I'm going to draw my free body diagram out. So here's what happens. Our tension goes off in this direction. So that's going to be 11,000 newtons. We would need to know some sort of an angle in here. You know what? We'll tell you that that's 17 degrees, which means down here it's got to be 17 degrees. So let's 17 degrees that. Force of friction comes backwards. Weight comes down. We're going to find the weight and the force of friction. That's the unknowns that we're looking for in this. So let's do our colors here, our components. You're going to have some sort of a blue from that and your force of friction. Those got to match off. And then you're going to have your pink from here, pink from there. That's going to match off. Actually, this pink, usually we say where it is, it's there. We can slide it over. So don't get confused. There's not two pinks. I don't think you will. So what that means is we're going to go blue has to equal blue and pink has to equal pink. So let's write down what these are. This is going to be Tx. That's going to be Ty. Sum of Fx statement. That's going to say that Tx is going to be equal to my force of friction. Tx is going to be T cosine of 17 degrees equals my force of friction. So my force of friction is going to be 11,000 cosine 17 degrees. So one step, one equation, one unknown, solve it out. You get 10,519 newtons. That's your force of friction. So that's the air friction that's keeping Tarzan from actually accelerating. So you might have something to do with an explanation about that. Sum of Fy, that's going to be pink equals pink, so Ty ends up equaling W. So T sine of 17 degrees equals the weight. So Tarzan's weight is going to be 11,000 sine of 17. So that will end up being 3,216 newtons. This must not be happening on Earth, because I don't know any Tarzan that can actually, because he'd be 321.6 kilograms. That's a pretty hefty guy to be swinging through the vines. So maybe this is happening somewhere else. I don't know. But there you go. 321 kilogram Tarzan swinging on a clothesline in your backyard.